And we're studying this problem. We see some xi's from a Bernoulli distribution. The xi's are going to be an element of either a 1 or a 0. So heads, tails, two binary outcomes. And we're going to be collecting some amount of data in the IID case. And the goal right here is to estimate p. Or infer p, do something with p, learn about p in some way. So estimate gives me a precise estimation. Some people like a hypothesis test on p, and we want to discuss all of that. I want to take a quick step back and discuss this term conjugate prior. So let me give you a definition. So we know Bayes is posterior of a parameter set. So I'll say theta are my parameters. Given your data is going to be proportional to the likelihood function of your parameters. Giving your data times a prior distribution, pi theta. So here's your prior. Here's your posterior. In some perspectives, this might be your state of ignorance or what you believe distributionally about theta before you see the data. After you slide it through the likelihood, the results are updated. And a posteriori, your beliefs are represented by this distribution right here. That is Bayes in a nutshell. Likelihood times prior, that's Bayesian statistics. If you want to make this an equal sign, you just normalize everything. And so equal is going to be likelihood times prior over the integral of likelihood times prior, d theta. So theta given d, theta, theta given d, theta. This is going to be over the entire universe. This isn't a function of theta in the denominator. And it's just normalizing everything, so everything adds up between 0 and 1. And so that's Bayes in a nutshell. Likelihood times prior. So if pi theta is an element of some family of distributions, so a family of distributions, so let me give you an example. I don't mean the exponential family. I don't mean classes of families over families. That's too broad. I mean like normal distribution. So what are the family of normal distributions? It's the whole collection of normals where you can plug in a mu and a sigma of your choosing. Once you pick a mu and a sigma of your choosing, you've specified an individual member of that family. So a very specific distribution, a family of distributions, e.g., f is equal to a normal, something like that. Not so broad that I don't know the behavior of the distribution, but rather a specific distributional type. So if your prior is an element of this family and your posterior is also an element of the same family. So if your prior is normal and your posterior belongs to that same family, it's a normal. It's a different member of the family. It's been updated. Then we say that, bless you, we say pi theta is conjugate. And you might say it's the conjugate prior. So what you might say is pi itself is conjugate. That's the conjugate family. And it turns out that this is always going to be unique. So it's going to be determined by the form of the likelihood function. The likelihood function is there, and there's going to be only one, if it exists, distribution that's going to be conjugate. And so that's kind of a nice thing, because it says what Bayesian statistics is in the conjugate case is it's just an algebraic system for updating the parameters in those models. So all you're doing is updating the parameters, not changing the class of models that you're working on. And so pi represents your beliefs on theta. Before you see the data, pi theta, where pi is a member of the same family, is your updated beliefs on theta. So same distributional form governing theta. And so that's really nice. If I were in the 1960s and all I knew was about a few different types of distributions, then I might want to stick to that class of distributions. So let's go back to our example right here, xi's or Bernoulli. Back to our example. Xi's come from a Bernoulli with parameter p. We get to see n instances. Our goal is to estimate p in a Bayesian fashion. Give me your posterior beliefs about what you think p is. So here's my question, is what's the conjugate prior for p? Now I can never answer this question until I write down the likelihood function. It has something to do with the likelihood function. It's a distribution that I multiply into it and I get back the same form of that underlying distribution that I'm multiplying in. So I have to stare at the likelihood, and I wrote down the likelihood for us. What is this? It's proportional to this thing. You can multiply by any positive number and it's still your likelihood function. In my graphics, I usually normalize it, but that's not a necessity. And so I have to look at this form and speculate about what I can multiply into this thing so that I get back the same form as my multiplier. And I don't know any way to do this other than just know your distributions and recognize it. So I kind of mentally go through, if I multiply by this, what would come out? So if I multiply that by like e to the minus p squared, some normal, it wouldn't look like e to the minus p squared anymore because I've got all that leading p exponentiated and 1 minus p exponentiated. And so it wouldn't have that form. And so what's the answer to this? I know some of you know the answer.
Beta.
It's a beta.
Yes.
And so yes. So p is beta. And betas have underlying parameters. I'm going to call them alpha and beta. These are hyperparameters. I know a couple facts about betas. I know that the expectation of p is alpha over alpha plus beta. So I also know the variance, and I might be able to look up some other moments. I know what the form of the whole thing is. So I know what the distribution looks like. Pi p looks proportional to p to the alpha minus 1, 1 minus p to the beta minus 1. You guys probably already know what a beta function is. I'll remind you, it's the normalizer for this distribution. It's aptly named. The beta function comes from a beta distribution when you integrate over it. So, beta function is this creature. I'm going to specify these two parameters. So beta functions are functions of these parameters. It's going to be the integral between 0 and 1, e to the alpha minus 1, 1 minus p to the beta minus 1, pp. And it turns out there's no analytical expression for this in the general case. And so while we write this down and we could go to MATLAB or we could go to our favorite software computing suite, it could give us a numerical answer for this when I plug in alpha and beta. Those are always estimated numbers. So you'll need a numerical algorithm to estimate that in the general case of alpha and beta. In integer cases, you could write it down explicitly. So there's a relationship to gamma functions. So this ends up being the ratio of some gamma functions. You might know which ones they are. Kind of interesting. So if you're studying in math class, you might want to know all this stuff, understand the relationships. But for our purposes, this is just the normalizer. It normalizes that distribution right here. So if I invert that thing and I multiply it by this will add up to numbers between 0 and 1. So when I say add, I mean integrate. Okay, so this is the conjugate choice. We can kind of recognize it that if I multiply this into this, I get something back that has the form of this. Right here. So let's just do that. Our posterior, given all of our data, I'll write down x, x1 to xn. This is going to be proportional to the likelihood, which is p to the sum of the xi's, 1 minus p, n minus sum of the xi's, times our prior. So p to the alpha minus 1, 1 minus p, is beta minus 1. And so we had motivated this distribution a little bit different last time. We didn't talk about conjugacy, but we just thought about distributions that live between 0 and 1. We're learning another nice property that when I simplify this, because it is the conjugate prior, this has the form of a beta. So this is p to the sum of the xi plus alpha minus 1. 1 minus p to the n minus sum of the xi's plus beta minus 1. So this posterior is proportional to that. And if I wanted to identify the underlying parameters, I just have to recognize them in the form of the beta. They're right here. So those are the parameters that underlie this distribution. So this is a beta with parameters, sum of the xi's plus alpha, n minus sum of the xi's plus beta. I usually call these alpha tilde and beta tilde, so they're my updated values. And so if I knew things about beta distributions coming in, my updated inferences about beta distributions, and I can tell you all the properties about this inference after seeing sum of the xi and n. So that's our inference. So let's just look at that. Of course, we do have to pick values for this. This is all just notational until I pick values for alpha and beta. So I'm going to state a fact. I stated this last time, that in some sense, and I have to tell you a little bit more about this, alpha and beta being equal to a half is optimal. I'll tell you more about this in a moment. So it turns out alpha equal to beta equal to 1/2 is generally a good choice. I have to tell you about these choices. And is optimal in some senses. And I'll tell you about this optimality in a moment. What do I mean? We'll see in a moment. I'm going to show you what this looks like right here. If you remember from last time, this choice, pi p, with alpha and beta equal to 1/2, lives between 0 and 1. It's beta. And it looks like this. So these things asymptote at 0 and 1. So I'm putting a lot of mass over there. So somehow my optimal choice, or my good choice, is saying, well, let's be symmetric about everything. I think that kind of makes sense. So I'm putting just as much mass over here, so I'm putting over on the right-hand side. So I haven't biased the analysis. But I'm saying something about where I believe P might live. And I'm saying, maybe I want to put mass on the poles. Now I want you to think about this. This can be a good idea. This is really a penalization for small sample sizes. What can go wrong in small sample sizes? So let me give you an example. So if I wanted to estimate P, I can look at some function of the data. Somebody help me out. How would you estimate P? So I want an estimator for P.
X bar.
X bar. So p hat is equal to sum of the xi's over n. And there might be a lot of good reasons why this is a good estimator. Okay, central limit theorem says something about it. It's a sufficient statistic. You're using all of the data. It's a consistent estimator. The question is it a good estimator on its own? And so imagine the case where p is very, very small. Okay, so let's say p is like 0.001. Definitely different from 0. It's possible something happens. And so imagine I go out and I collect 10 samples, 20 samples. Let's say it's 30 samples. Let's say p is 0.0001. I go out and I collect 30, and I believe for my Stat 101 class, 30 is good enough. I'm going to estimate things pretty well. And I end up seeing out of those 30 instances all zeros because p is very small. So my estimator is 0. And the question is how precise is that estimator? Like, can I quantify uncertainty about it? And a typical way to do this is to compute the variance in everything. And so you might compute the variance in this. P hat, how would you compute it? How much variability is there in there? What's that? What's that? So it's stochastic, right? It's this random thing. It's going to vary around a little bit. So how would I estimate the variance of p hat?
Just the same way, right? Sample variance.
Yeah, so maybe the sample variance. So what is it?
X minus mu squared.
There's no mu.
P hat, rather.
P hat. One minus p hat. Over n. Let's go back to Stat 101. So what's the variance of an xi? So variance of xi, so I might be estimating this thing and I might be saying, hey, this is some quantification of my variance about this. What's the variance of each xi? P times 1 minus p. You can do the rest. And so this is really just this thing. P times 1 minus p over n. That's the variability of the system. And so what most people will do when they pivot is they'll throw in p hats for that and try to estimate it like that. So I'm going to say that if I've got a good estimator for p, then I'm just going to plug it into this equation. So maybe our variance can be estimated by, can't use this right here because I don't know p. If I knew p, I wouldn't have to even discuss the variance of this. So I might estimate it by p hat, 1 minus p hat, over n. So I plug in my estimates for it. This is called pivoting. You build a confidence interval this way, this is pivoting. So this is kind of the asymptotic way of doing all this. And so my interval estimate, so confidence interval, might be this, p hat plus or minus 1.96 square root p hat 1 minus p hat over n. So that's my confidence interval. Where's 1.96 coming from? I'm using a normal approximation. You might say, well, maybe this is good because you've got 30 observations. So I was told if I got 30 or maybe 31, then I'm sure. And so it turns out if p is really small, this turns out to be problematic. And if it's very large, it's problematic for the symmetric reason, so that you get a whole bunch of ones. And so what would I get if I saw 30 zeros? I'd get that being 0. And I would get that being 0. And so my interval would be 0, a point. And it's a terrible estimator. It's a terrible inference to say, well, I think that the answer is 0, not a bad guess, and that's all I think it is. And so we see a fundamental breakdown in asymptotic methods right here. And so it turns out anybody that was a frequentist and studied this for any amount of time would end up telling you that all of the asymptotics are breaking down because of the boundary condition, that I'm shoved up against the boundary. If p happened to be 0.5, this wouldn't be so bad. This would work okay. And so how good is this method depends on what p actually is. And that's a little bit of a nuisance. I want my methods to adapt to whatever p is, true p is. But this isn't a good answer. I'll leave this as a question, and I'll just say that I don't think so. I don't think that this is a good answer.
So why did we drop p hat from values of p hat is equal to p? So if we knew p, how would we be calculating that?
If I knew p, I would just tell you what p is.
Yeah.
I wouldn't even calculate variance, right?
So why did we, I'm asking why did we drop the hat from values of p hat is equal to?
Because this is a function of the parameter space right here. If I look at the expectation of p hat, it's p. It's not going to be hats. Then you pivot.
Okay.
Make sense? So expectations, variances, are types of expectations or functions of the parameter space, not of the estimator. So the prior that we're looking at is going to penalize answers like this. It doesn't like an answer like this. Bayesian is going to say, let's penalize things around those zeros and ones. Don't say the answer is 0. Put a little bit of mass over on 1 as well. And that's that horseshoe shape. And symmetrically, it does it on both sides. So it's penalizing the endpoints. Let me actually show you what happens if you compute that interval. I'm going to have you compute this for homework 1. So if you get bored, you want to get started, produce my simulation. If you want to wait a couple days, I'll have instructions on it. So binomial coverage. Just going to wait for a second. Let me actually change this real quick. Let's not get ahead of ourselves. If I end up computing these intervals, and I count how many times does it cover the true p, I can come up with a frequency. So what I'm going to do is I'm going to collect a data set with a particular n. My n in the simulation is 100. No, sorry, 30. And it's 30. So what I'm going to do is for a particular value of p, I'm going to sample 30 instances, and I'm going to create an interval. Okay, so I sample 30 instances with whatever p is. I create this interval, and I see, does this interval actually cover true p, what I use to generate the data. And if it does cover, I call it a 1. And if it doesn't, I call it a 0. And then I repeat the process. So I go and I collect, for the exact same p that I had before, 30 samples, compute the interval, I check to see if it covers, and I record that as a 1 or a 0. And then I just calculate the frequency of coverage. So this interval right here is supposed to cover 95% of the time. That's where the 1.96 comes from. So it's supposed to. Covers about 95% of the time. And so in order to make this plot, I just changed p all the way through. So I just threw p on a grid, made some sort of refinement to that grid, and I just repeated that process over and over and over again. And this is the result I got right here. Now you might ask about this jagged line right here that's running across. It looks like it's running through about 0.95 if you look at the y-axis. Most of the time it's kind of undercovering it, overcovering it, but down by the endpoints it's horrible. It's not covering at all what you think. So if I'm about under 1% or over 90%, my coverage rate starts to deteriorate quite quickly for this reason that I gave you before. That if p was very small and the sample size wasn't large enough, we would get a nonsensical answer. Towards the middle, not so hard to do. Everything works out pretty good. You might think that the jagging of the line is stochasticity in my simulation. How many times did I repeat this for each one of those dots to get the frequency? I repeated it 100 times. And so you might say, well, crank up this number right here and make it 10,000. Make it 1,000 or something like that. It turns out if you do that, I'll make it run 10 times longer real quick. We're going to get the same plot back, approximately. So that didn't go away. And if I keep cranking up n, that's not going to deteriorate. Or if I crank up the iterations, it won't deteriorate. And so basically near the endpoints, we have an estimation problem. If I cranked up n, however, let me just crank this down, 100 iterations seems to be enough to see what the pattern is. If I crank up my sample size, things improve a little bit. So let's make that 100 samples. And I'll run that again. And these lines right here came up a lot. So 0.55, so not too bad over there. Let's crank it up again. 1,000. There's our answer. We're kind of cutting through 95, and so I need a big sample to start making this method work well. This is an asymptotic method, probably not your favorite technique. And most people would say there's an exact interval. Why don't you use the exact interval and not the asymptotic one? I think that that's a fair statement. It turns out it's not as bad as this one is performing. So I need a lot of sample to start bringing this thing up towards 95%. Turns out that if I wanted to be, if I were within a percent of the endpoint, and I wanted to be within 1% of the 95% limit, 1% to the nominal rate. I'm saying this is a 95% interval. I want it to actually be a 95% interval. Not in some mathematical class they told me it was. I forgot to check and see what it actually is. It turns out it's not 95. So if I wanted to guarantee I was within 1% of the nominal rate, when I'm 1% out from the boundary, it turns out you need something like 9,000 samples to get you there. So that rule of having 30 is not very good when you're near the endpoints here. So this isn't a very good interval. Question is how does a Bayesian address all this? What they do is they take their posterior distribution and they collect an interval out of it. So let me first show you what the posterior distributions look like, and then we'll come back to the Bayesian analog of interval estimation. So we'll go back to this piece of code. This is my sequential code. This is the one I want. It's going to take in inputs p, alpha, beta, so true p. I need to simulate the data somehow. That's the only place I'll use true p is to simulate the data, and I'll plot it for reference, but I never use it in any of my answers. I have to take in the hyperparameters, alpha and beta, underlying my prior distribution. I have to state how many times I want to flip the coin in this example. And I've also got this parameter epsilon. I'm going to talk a little bit about that for a moment. What I'm going to test in a classical setting is this hypothesis that's illustrated in green. So the hypothesis says that H naught, the null hypothesis, is that P is equal to some specified value P naught. And I'm defining P naught to be true P plus epsilon. So epsilon is my difference on the truth. And so if epsilon were 0, then the null would be true. P is P naught. Okay, so epsilon is my degree of difference with the actual truth. And I want to show you how the p-value behaves for doing this analysis. And so the p-value, somebody define that for me just real quick. So p-value.
Probability of observing your results or more extreme under the assumption of the null hypothesis.
Perfect. So probability of your results or more extreme given the null is true. So we're going to look over this proxy of more extremity. The alternative tells us the direction of more extremity in here. And so you're going to chase the tail direction. And so I'm going to chase the left-hand side because that's the way the alternative is pointing. So if you've ever taken any inference class, somebody's carried you through this calculation. I'm not going to use the asymptotic p-value, the normal one. I'm going to actually use the discrete nature of this distribution. And so all I have to do is sum up x goes from 0 to whatever I observed. This is sum of the xi's, if you will. I goes from 1 to n. This is my observed. And now I need to sum it over my sampling distribution and choose x, p to the x, 1 minus p to the n minus x. And I'm going to let x vary all the way up to my observed count. So I know the distribution of the observed count, it's binomially distributed. So this is the corresponding p-value calculation. So if you need a refresher on p-values, go look at Wiki. We've got a lot of examples. We'll keep looking at some of them. But basically, if epsilon is very large, I want to reject. I want a p-value that's small. So Neyman and Pearson say that under some alpha level that needs to be pre-specified that controls the type 1 error, if I reject the p-value, if it ducks that number, I'll have maximal power in my analysis. Talk about that later. So, but ultimately I'm just using this statistic right here. It's supposed to have some power to detect against the null hypothesis and reject it accordingly. So I'll show you that code. I'll post it online for you if you'd like to play around with it, but let's just simulate. So I'm going to plug in some values. Okay, so let's say true p is 0.7. My prior is a half-half beta. I'm going to flip the coin 100 times, and my epsilon is 0.3. So epsilon's pretty big. P is not equal to P naught. P is definitely less than my specified P naught. P naught is P plus epsilon. So it's definitely left. We want to reject. So we'll see these two different lines of thinking. So I flip the coin exactly once. Start that again. So before I flip the coin, I haven't done anything with the coin. Here's my prior belief. So I'm penalizing the endpoints and saying, if you have small sample size, give the other side a little bit of weight. I'm going to assume that it's possible that the coin isn't, all zeros. I'm going to believe that P could be 1, and I'll place a little bit of mass there. Then I flip the coin, and I end up getting my likelihood function. So the likelihood function is just P raised to the 1, 1 minus P raised to the 0. That's that straight line. My posterior distribution, which is the superposition between the prior and the likelihood. So all I'm doing is I'm multiplying those two numbers in the prior and the likelihood, and that's the posterior. And then I normalized everything. And so it looks a little bit different from the likelihood, but not too different. A little bit of penalization. I flip the coin again, and this starts to evolve in bend. So my posterior inference is what the Bayesian's giving you is you're giving you this curve. Now you got to decide, what do I want to do with the curve? So the Bayesian answer is really the curve. It's posterior. It's always a question of where's the information in that thing? How do I want to interpret it? Over on the left-hand side, I have the relative frequency, so I'm just counting relative frequency on everything. So true P is 0.7. Relative frequency is a little bit high. Just happened. My p-value, however, so I'm plotting sequentially, a p-value is tanked towards 0 really quickly. So it's rapidly gone down. It says reject the null in favor of the alternative, and the alternative says that P is less than P naught. P naught is true P plus epsilon. So it's true. The p-value has done the right thing. It says, nope, not P naught, it's something smaller. That's the answer. The Bayesian, however, is quantifying for you, I think P's in here. That's my probability distribution of it. This massive part of the distribution seems to overlap the truth. And here's what a Bayesian does to get a credible interval. If they want a 95% interval, they look at a region right here that contains 95% of the mass. It's a posterior distribution, so if I integrate across, it's going to integrate to 1. And so I can integrate over any region that has 95% of the mass, and I can say that is a credible interval or a credible set. So they're not unique. I could take the 95% side right over here, 95%, and that would be my interval. Or I could come from the other side and collect 95%, and that's my interval. Same thing can be done with a confidence interval. All I need is coverage, and there's a lot of different ways you can cover. So I made specific choices about how to cover. And so confidence intervals and Bayesian intervals, which are called credible intervals, are not unique. You need to specify something else to make them unique. So you might say, I want the shortest possible interval. And so for a Bayesian, that would mean the highest posterior density region, the region where most of the mass is. And that would give you the shortest interval. That's what it means to be highest density. You have the most mass in the shortest region you can find. And that would be unique if this distribution wasn't uniform. So if it didn't have any flat spots in it. It was properly identifying the parameter space. And so Bayesian answer, a little bit different. So a credible interval is an interval, and I'll call this lower b for lower Bayes and upper b for upper Bayes, such that the integral of the posterior distribution over theta between lower Bayes and upper Bayes is equal to alpha. And so I should specify an alpha level credible interval is this. So it's a region such that I integrate under the posterior. That's what that'll always mean throughout the rest of this class, pi theta given data, posterior distribution. Is the mass defined by these bounds adds up to alpha. Okay, whatever that number is. So maybe this is 0.95. So this is typical choice. So Bayesian would say I'm 95% probable. I believe it's 95% the case on a probability scale that true theta lives between LB and UB. So let me show you the results from our analysis. We'll go back to binomial coverage, and I'll show you what the credible intervals look like. And I've picked my hyperparameters in here to be a half and a half. So I can change those if I wanted to. Gotcha. Let's turn down the sample size a little bit, back to 30. So, Stat 101, they'll say a typical sample. We can start ignoring that now because we know 30 is not enough near the endpoints. But the Bayesian has a very different answer. So the interval that I form, and what I did is I took 2.5% of the mass to the right and 2.5% of the mass to the left, and I just threw it out. So I didn't actually look at an HPD, a highest posterior density interval, but I came pretty close to doing it. And so if n is 30, that beta distribution that I get looks pretty normal and it's pretty symmetric, but there is a little bit of skewness to it. And so I came up with an approximate interval that was easy to compute, and I looked at my coverage rates. And that's the red coverage rate for the credible interval. And so those penalties around the bounds, 0 and 1, that penalized space is pushing those things up. And that's what it's really doing. Turns out, Jerry Brown over at UPenn proved that this is the optimal analysis here. And so you can't beat my coverage rate if I use a half and a half and I operate as a Bayesian. If I came up with the HPDs, you would do a little bit better, but you wouldn't be able to visually detect it. So it's pretty sloppy and it did something pretty good. And I kind of like that answer. And so turns out in this analysis, the Bayesian is the optimal frequentist. So if I want to interpret my intervals as frequentist covering, I have to have some properties out of my prior to get that. Turns out this choice is very good for that. That's a hard thing to get in general, optimal coverage, but it turns out Bayesians can be frequentist as well. So what frequentist property am I looking for out of my inferences? Intervals that cover at some relative frequency. That's a frequentist property. So if you say you're a frequentist, you need a frequentist property. And so I'm a Bayesian, and now I'm a frequentist as well. So we can get out of our minds that there's frequentists and there's Bayesians, and there's no overlap. Because this example shows you that my Bayesian inference has very good frequentist properties. And so that's at least the answer right here. We could have changed those, what the prior looks like right here. So I could do it again, and I could say, hey, let's bias this thing. Let's make that like 5. Well, let's not bias it. Let's just plug in 5 and 5 right here. I'm going to crank up some numbers. So the expected value is still a half a priori. So I haven't biased anything, but I've certainly changed the variance of that distribution. We can look at it right real quick. If we want, I can change this to a 5 and a 5 and see what that prior looks like. There's the prior. So it's pulled down the horseshoe, and it's centered it at a half still, and it placed most of the mass towards the middle. So I can look at what my inference is on. What we'll notice is that the likelihood and the posterior distribution are farther apart from each other than they used to be. So it didn't close in on it as fast as possible, really fast. So it's a little bit slower to converge to something. I've changed the variance. I think that the answer is closer to the middle. The answer is actually 0.7. If I let this run for a very, very long time, those curves will get infinitely close to each other. If I let it run for infinity, they'll be right on top of each other. And so even if I make prior choices that aren't that great, the data can start to overwhelm them. Let's look at the coverage. Binomial coverage, 5 and 5. We'll see how we do. My Bayesian answer is not so good anymore. So why? Because I ended up shoving it towards the middle, so it estimates really poorly on the endpoints. And so the hyperparameters do have an influence. So we have to start coming up with principles on how we come up with those hyperparameters and what these priors are. But what we notice is the Bayesian answer can be good or it can be bad, depending on how you calibrate that prior. Okay, any questions about this so far?
So, I have two questions. So first, what do you mean by wall confidence interval?
So that's this one. This is the asymptotic walled interval.
Okay.
So this is what this is called right here. So this is the walled interval. So here's something that people will do with this. Alan Agreski has a prescription for operating with this. He knows this is bad. So he says to do something. Does anybody know what the Agreski prescription is? This is a typical thing that you'll see people do in statistics. Agreski is a person. So Alan. I don't know if he's an AN or an EN, I'll just take a guess. So Alan Agreski says, take your data, okay? So I'm going to say that's X. It's going to be X1, Xn. So that's what you observed. And he said, and add a 1, and a 0, and a 0. So he said, add 2. Add 2 successes and 2 failures to the set. Good prescription. What's he doing? He's penalizing the endpoints. So the Bayesian says don't add 2. So add 2, add 2. So add 2. Add 2. So negatives, successes. The Bayesian says something else. So the half-half prior says to add a half and a half. So the Bayesian says don't even add a full sample to each side. Add a half a sample. That's really what's going on here. So if I look at everything, I look at this, at the end of the day, here's my thing. What am I doing? I'm adding a half maybe, and a half over here. So it's like Alan Agresti's prescription. If you ask Alan, what are you doing? Like, what is that branch of statistics? He'll give you different answers depending on the day. So he'll say, it's like a Bayesian penalty to some people like me. And to other people, he says, well, it's a heuristic that works very good. And so, and you'll hear people argue about this. Is this Bayesian? Is this not Bayesian? What is this? And Alan's basic thought is, I don't care what you call it anymore. Just do it, or do something like it. And if you want to add a half, add a half. So there's been a lot of fights over, is this thing Bayesian right here, is it not? And it really doesn't matter. I like to think about it as a Bayesian thing. This would be like adding 2 and 2, alpha and beta being equal to 2, and that doesn't work nearly as good. We can look at that answer. So 2 and 2, and see how well we get. Does okay. It's better than the other answer, but it can be improved even more if I go to a half and a half. You might say no penalty. How about no penalty? A 0 and a 0. You can try that as well. It won't work as well. How do I know? Because Larry Brown told me. So 0 and a 0, not quite as good as well. So that half and a half is a like magical thing. That's pretty cool. And the real take-home point is the Bayesian is the better frequentist, which is really cool. Please.
Should we say again how we calculate coverage rate?
All I'm doing is I'm taking my interval. So if I'm the Bayesian and I ended up coming up with my posterior, I plucked off 2.5%. So I have my interval. I have a prescription for coming up for an interval. I have true P, what I use to simulate the data to form the endpoints of my interval. And I check to see if my interval has P in the middle of it. If it's in the middle of it, somewhere, I call that a 1. If it's outside of the interval, I call it a 0, it did not cover. And so their interval under the frequentist interpretation is supposed to cover. So I check that, how often it covers. The Bayesian answer is they think P is actually in that interval. It's not necessarily coverage. It's your belief for where P is, but it can also be treated as a coverage interval if it has the right asymptotic properties, if it actually covers.
But when you said in the middle, wasn't that the highest density one?
It's not quite symmetric. So here's my point. So if I go back to this thing right here, that posterior distribution, that red line is not symmetric. It does limit to something that's symmetric. So it's getting closer and closer to symmetric. So I took 2.5% to the right and the left, and it turns out that interval might not be exactly symmetric around my inference. As n cranks up, that thing looks more and more symmetric.
I mean, the goal is to choose one with the highest density with respect to the true value, or?
That's one such choice, and it's a very good choice. I didn't quite do it. Why not? Because I was lazy. I just like 2.5, quick interval, bang. Coming up with the highest density interval is a harder computation, because I have to actually measure where the density is highest. It wouldn't be that hard in this case, in a one-dimensional case, but it can be hard in a higher dimensional case. But I did it just because it was simple, and it still worked out.
So just measuring the middle point and
Took 2.5 from the left, threw it away. 2.5 to the right, and I threw it away. And if that is big, that's very close to a highest density interval. So that's basically what's going on right here. Bayesian thinks a little bit differently than the classicist. You might notice that if I ended up doing this same example, but I plugged in an epsilon right here that was like negative, then I shouldn't reject the null, because P is not less than P naught. And so we'll see what happens right here. I run everything. And the p-value starts climbing towards 1. One thing you'll notice, the bigger I make epsilon in magnitude, the faster it converges to 1 or 0. So it's really the rate at which p-values decay or climb that's really inferentially important. We'll talk about that later in a couple months. So I think what would be helpful is we come back and we do another example next time. Go through this all again. And so if you want to look at the normal conjugate case, that's where we'll pick up next time, and we'll talk a lot of variants of that problem. Just repeat this whole process. We'll do this on a couple different distributions, and later on we'll start getting fancy with everything. Sound good?